Hi friends, welcome back. This is Santosh Kumar. Today we are going to discuss about the complementary root blockers. We'll see the comparison among all RH, Bode, root, polar plot, Nyquist plot. Okay. Friends, when we started the control system, we have seen two things, and I think you will be agree with me. From the chapter 1 to the end, we were dealing with the transfer function only. So control system is nothing but the name of find out the transfer function. Each and every unit you have given with the transfer function, you are doing something with the transfer function only, isn't it? So two types of thing we have seen, the closed loop transfer function and open loop transfer function. Some people have doubt in these two things also. The open loop transfer function is, when I say the open loop transfer function, this is G of S, H of S always. Okay, this is kind of, see, like this. This is your system. Now this is your feedback element, but this is not connected here at the mixer stage. Okay, in this case, this transfer function of the system is nothing but the open loop transfer function. Okay, now if HS is 1, that is a unity feedback, then it's good that you'll get the GS. Otherwise, only G is nothing but the forward gain of the system. Forward gain of the system. Gain of the system is nothing but G of S. Okay. Now, what about the closed loop control system? Yeah, surely you will close it here and then you will get the new transfer function, that is, here I'm writing G1 plus G of S, H of S. Okay, you are familiar with this, but many of you have maybe confusion. What is the open loop transfer? Open loop transfer function is not G of S simply. Okay, the open loop transfer function is G of S, H of S. If you have unity feedback here, means the feedback element HS is 1, then only the open loop transfer will become the gain equal to gain, the forward gain of the system. But open loop transfer function is not G of S. Remember this point always. Okay. Okay. Now based on this, we have seen some analysis. Analysis for what? We were discussing about the stability, isn't it? So we have some methods. We started our unit means to analyze the stability from the RH criteria, then root, locus, then Bode plot, then polar plot, then Nyquist plot, isn't it? This all techniques to find out the stability or to deal with the stability of the system, isn't it? Now one more thing before I'll come there, whatever we are studying or whatever we studied in the control system from first unit to the last unit, everyone for the LTI systems only, the linear time invariant system. Okay, all these systems are linear and time invariant. Whatever study we have done is for this only. Okay, so remember this point, note down. And you know very well what is the LTI system. This is the if you studied the signal and system, everything will be clear, so I'll not going into the deep of that. Okay, now one by one we will study this. Okay, so for the stability analysis, what we have seen yet is the RH criteria, isn't it? And the root locus also we have seen the root locus. Okay, all this technique, these two techniques basically, actually the RH deals with the characteristic equation, means to proceed by RH you need to have the characteristic equation, isn't it? And the root locus deals with open loop transfer function, means it will always deal with the open loop transfer function, that is this. Okay, not this. Okay, This is only when you have the unity feedback. So why I'm going to separate these two things? All these two techniques are not the frequency domain. Now this, whatever I'm writing here, all are the frequency domain analysis. In the frequency domain, we changed the Laplace or the A's domain, whatever given. The transfer function you know very well. In the definition of transfer function itself, what is given there, the transfer function of the output divided by the transfer function of the input, provided the initial conditions are 0. So everything will be there in the S domain only, the Laplace domain. Okay, so for these techniques, whatever I'm writing here now, the Bode plot, the polar plot, Nyquist plot, all these were based on, the frequency. What we have done here, we replaced this A's by j omega. Now you may ask this question, why j omega? Why not S equal to j omega plus sigma? Why not this? See friends, the answer of this will be, we are looking for the frequency domain analysis, isn't it? We are dealing with the time domain signal. Here I can say this is the time domain partially, okay, because you converted everything into the S domain, means Laplace domain. Whom you converted in the Laplace domain? The time signal, the time functions, isn't it? On the system, you applied some time input and you get some time output, means in time domain. Okay, now to find out the transfer function, the technique is you have to convert into the the S domain. Okay, you did. So this to study directly based on the S domain, isn't it? We are dealing here in the S domain, we call it the, means we are doing indirectly the time domain analysis only, but here we are converting into the frequency domain. Frequency domain means you need to come in omega, okay, but S equivalent is j omega plus sigma. S equivalent is j omega plus sigma. So if you are just putting S equal to j omega plus sigma, it means you are going into the equivalence of the Laplace, not the frequency domain. Okay, and you know very well, if you want to convert the time signal into frequency domain, you will use the Fourier transform. Is it okay to you? The Fourier transform you will use to convert the time domain into frequency domain, the Fourier transform. Is it okay to you? You have time signal here, the time function you have, but in the form of Laplace, isn't it? Now you are looking for the omega, isn't it? Means you need to go in the Fourier, means you are going to convert this t into Fourier transform of it. So everything will be in the frequency domain. Okay, so the equivalence of this S, you have S equal to j omega plus sigma, but this is not the complete frequency domain. So if you want to convert this into complete frequency domain, what is the relation between Fourier transform and Laplace transform? What is the relation? If sigma equal to 0, the Fourier transform is nothing but the Laplace transform. If sigma equal to 0, then Fourier transform will become Laplace transform. Okay, what it means? Means whatever transfer function you have given, just put S equal to j omega. Now whatever you will have, that will be in frequency domain, isn't it? Is it clear to you? Here, instead of this j omega plus sigma, if this sigma is 0, means indirectly you are coming into the frequency domain. Okay, so that's why we are going to do, we are what we are going to do is we are putting S equal to j omega. So your system will become in complete frequency. domain. Okay friends, so these are the techniques, and in these techniques, in these all techniques, we are dealing with the open loop transfer function for all this. In the root locus also we are dealing with the open loop transfer function, but for the route or weights we are dealing with the characteristic equation. Is it clear to you? Very good. Now we'll see today the complementary root locus. Very important. So important for whom? For the IES fellow. EAC exam, it's bit important, but for GATE exam it is not that much, because if you will observe the previous year papers from 1992 to 2017, you will hardly find there only 2 or 3 questions, hardly 2 or 3 questions. Okay, but though we are dealing in miscellaneous topics, so I need to cover this complementary root locus. Friends, whatever we have seen earlier, that was the direct root locus. That was direct root locus. Okay, in the control system generally we are dealing with the negative feedback only, isn't it? So for the negative feedback, the characteristic equation will be always like this. For the negative feedback, here it will become plus. This here the sign will be plus for the negative feedback. You know very well why. Okay, now what if you have positive feedback? So in the case of positive feedback, you will have here like this. This is the condition for positive feedback. This is positive feedback. Okay, so what we have done yet, we have done the analysis, means root locus analysis for the negative feedback. We have done for this the root locus analysis. Okay, but if you have the positive feedback, you will have the analysis, that is the complementary root locus or inverse root locus. Okay, here. So all for positive feedbacks we have complementary root locus, and for the negative feedback you have the simple or direct root locus analysis. Now here 2 things will be there. See, so come here, I have 2 scenes related to the K value and the feedback. Okay, in the first case, the K, this is the system DC gain, and this is the positive, suppose, and your feedback is positive feedback. So in this case the characteristic equation will be, you will agree with me, 1 plus GH equal to 0. If this is the positive feedback, means negative will come here, and just we discussed this is nothing but the complementary root locus or inverse root locus. Okay, but if you have the negative feedback, your system will be GH equal to 0. You have positive sign here. This will be direct root locus. Okay friends, so till now what we have done is wait a minute, let me change. Here we have seen this yet. Whatever root locus earlier we have seen, that was the direct root locus. The negative feedback and the K values were positive there. The gain values were positive. Okay, so this part is already done, isn't it? Now if for the K value and K values are positive, if you deal with the positive feedback, you will deal with the complementary root locus. Okay, now let me show you. If the K values here, the K values are negative, so if you have the positive feedback, means it's minus GS equal to 0, isn't it? And the K value related to this parameter, so when the K value will be negative, this will become 1 plus GH equal to 0. Are you getting me? So if this is 0, and this plus sign here, so this belongs to direct root locus. If k is negative, you have the negative feedback itself, and your k is also negative, so this will not the direct root locus, it will become here, see, the negative feedback means plus gh equal to 0. Now this is negative, this term means k belongs to this category or not, it will become 1 minus gh equal to 0. So this is minus sign, and this will become complementary root locus. Remember always. So for the complementary root locus, we can have two things. Where are the complementary root locus? See here. We may have positive feedback, and definitely the k value is negative. Two things we may have. Number one is, for the complementary root locus, we can have two things. The first is the positive feedback. But the second is, where is the CRL? Here. The second one is negative feedback. Sorry, the negative k value. Okay, so for the complementary root locus, two things you will always remember, and those things are either you have, the positive feedback. Positive feedback, or you have k value negative. Okay friends, this two condition, and in or I'm telling you, this is not and sign I'm using here, this is or, any one of them. Okay, not both. If both will be there simultaneously, means we are here, this is the direct root locus. So this is very important point. Okay friends, so now what is the inside of the C? So now the transfer function or the characteristic equation I'll take of the positive feedback, that is 1 minus GH0. Okay, so this is the open loop transfer function we are using, so keep here, this will be 1. So find out the magnitude. Magnitude will be 1. What is the angle? The angle will be now 0 degree or 360 degree. Okay, so that's why here we will write now 2q into 180 degree. In the direct root locus, we have seen the odd multiples of 180 degree. That is 2q plus 1 divided by, that is the difference seen. The angles are in the even multiplication. Okay, and in the direct root locus, they were in odd multiplication. The magnitude condition is same, no need to worry. Always we have to check the magnitude, whatever we were checking there in the direct root locus. Okay, now the rules are same. All rules, direct root locus. Okay, so for the complementary root locus, the rules are same except few things, and the things are here. Now if you'll find out the angle of asymptote, you will use 2q into 180. Everything will be same as it is, p minus z. Q is nothing but from 0 1 p minus z. Okay, here I'll use the 2q. Okay, this is one thing, the thing number, the point number 1, and the second point is, now to find the RL branches, rule will be changed. RL branches rule will be changed. RL branches rules will change. Okay, so what is that? See, this is your, the S plane. Here you have some poles. Okay, now if you want to find out the root locus branches on real axis, RL branches rules, RL branches on real axis. Okay, so here let's take this as 0 and this is -1, -2. So in the direct locus, when we were discussing about where the root locus real branch, this is, let's take it real branch or axis. Okay, try to understand this. Okay, so this on the real axis, see real axis, yeah, suppose you are looking to find out the root locus branches on the real axis. If you are here, you'll observe into the R plane, and if number of zeros or odds are odd, then only there will be root locus branch. But here you will see the even numbers, even number of wholes plus zeros. We will understand what I'm saying is. So here no CRL branch will be there. Here at this point, yes, definitely this is CRL branch. This one is CRL branch definitely, but this is not. So at this point also, here we are getting 0 only, so this one will be also the CRL branch. So this is just opposite to the the direct root locus. I hope you are getting me. Now the third point is the phi d and phi a, angle of departure and angle of arrival. There we have seen the formula 180 degree plus phi. Here everything will be 0 plus phi, 0 plus phi, and you know very well what is the phi. For the departure, it will be phi p minus phi z, and for this it will be phi z minus phi p. I hope this one is clear to you. So these are some changes. Rest of the things are equal to each other. Okay, for the DRL and for the CRL, the rules will be same, symmetric and all whatever we discussed, only these things will be changed. Okay, now I'll take one problem. This is the GATE 2005 problem. Here is the question. This is 2 marks 2005 question. GATE 5, 2 marks. And a unity feedback system, sorry, this is not a unity feedback system is given. Okay, GS this, the correct root locus is. Here are the options. So if options are given, you will do in exam very carefully. So one more thing related to the transfer function. The right thing to write down the the transfer function, this A's should be in positive form. The right format, or I can say the general term to write the transfer function, is nothing but like it will be S plus minus whatever it is here, S plus minus T2, kind of like this. S plus, here suppose let's take it N1 plus minus P1 plus minus P2, kind of. Okay, so this is the right format. Always write like this only. So this is given here, this S is given minus. First we will convert into the standard or general format. So you will have GS, this is K minus S minus 1 and S plus 3. Now we discussed that in the complementary root locus, the K value will be either negative or the positive feedback. Is there anywhere mentioned the positive feedback? Note down this point. If the feedback is not mentioned, it means you need to consider it negative feedback always. Always negative feedback. By default the system is negative feedback. Here they define only unity feedback but not positive or negative. So this is negative feedback given. Note down this point. Okay. Now the second point is you need to convert the transfer function, any transfer function, into the standard format, and here is the standard format we discussed. Okay, after converting this we are getting the K value negative here. So this k value indicating, see, here you get the k value negative. What this k value negative indicating? You know the idea now. This is the complementary root locus. So if you know the complementary root locus, now you know each and everything. You can easily plot the root locus. Now I'll start the plotting. Okay. So here I am. Okay. Is equal to 1, that is 0. Here my 0 is equal to 1. Here is your pole, and here is another pole, that is -3 and 0 and 1. Now let's find out the RL branches. So for that I'll take the pen, this. Is there any RL branch? And that is CRL branch. No, because number of poles, summation of poles and zeros into RHS of this point is odd. So here I do not have. Yes, here I have. Because at this point in the RHS you have two number of sum of poles and zeros. So definitely this is the even number. You will have here the CRL branch. CRL branch. Rest of the thing will be as it is. Okay. So now see, what about this? This is also the root locus branch. Okay. This one also, because at this point nothing is you are getting, 0 you are getting, that is also even we are considering. So this one is also your branch. So in these two options you can get this thing, but this is not our answer. This is the direct root locus they have taken. Okay. Now we'll find if two poles are meeting. If these two poles are coming like this, definitely you will have the breakpoint for this question, isn't it? So when you will find out the breakpoint, you know very well how to find out the breakaway point. Okay. So the breakaway point for this question you will get is 3 and -1. So 3 is not valid point. Here is 3. We are not having two poles. Okay, so breakaway point I'm talking about. So here we do not have the breakaway point. So breakaway point will be at -1. Yes, we can have here. Here we can have. Okay, so now you will find out the, see, as we discussed in the root locus, if two poles will meet, they will bifurcate by this formula, isn't it? So this is 180 n equal to 2. Two poles are meeting by 90-degree angle. They will leave like this. Like this. They will come here. Okay. Here two poles are meeting. Again, one will go to this side, because ultimately they have to reach to 0, and one will go to this side. Okay, this will be your root locus diagram for this question. That is the option C given here. So rest of the things you can do it. What my intention was, you know, I need to clear all these things. And what is the complementary root locus? Now I think you are aware with this. You know the formula, the rules. What is the departure angle, what is the asymptote angle, each and everything you know. So easily you can calculate for this, and you can further study this question only. Okay. So today up to the root locus, and that is the complementary root locus, it's enough for the day. In the next class we'll meet again. I think that will be the mirror discussion of the control system. Okay. We'll meet in the next class. If you are the new student, please subscribe the Gatematic. It will be really helpful to you. We'll meet in the next class. Till then, take care and bye.